Using the MM1 formulas to model a waiting line isn't in and of itself too terribly difficult. The MM1 formulas, however, are built upon the parameters lambda and mu, and the one thing that's challenging about those formulas is making sure you have the correct lambda and mu. This short problem is basically a riddle in that. Now, what do I mean by that? Oh, it says cars arrive at an average of 10 minutes apart. Now, lambda, I keep saying you need a lambda and a mu. Lambda is the mean of the customer arrival rate. And here it's talking about cars that apparently are customers. Oh yeah, they're customers at a toll booth, right? So there's information about lambda. And exponential service time averaging 1 minute. Oh, that's mu. Mu is the mean of the exponential distribution that describes the service rate of the system. So that's information about mu. The question is short. It's just asking how often is this toll booth idle. That's a pretty simple MM1 formula. That's nothing more than capital P for probability, 0 meaning the chance that there is nobody in the system or the proportion of time the system is idle. The only thing we need to do is just say 1 minus, you can look up this formula, it's just 1 minus lambda over mu. Oh, so you might have tried this already. All right, well, you know, yeah, okay, so that's 1 minus the 10 divided by 1, or 1 minus 10. 1 minus 10 is negative 9. Wait a minute, this is not working at all. What proportion of the time is a toll booth idle? Negative 9. Cars arrive at an average of 10 minutes apart. That is information about lambda, but lambda isn't 10. To get MM1 formulas to work correctly for you, you have to remember there's a very particular definition for lambda and mu. Lambda is the average number of customers to arrive in some time interval. Oh, for instance, you say some time interval, yeah, like an hour. Lambda, when we're talking about customer arrivals, we're always talking about numbers of customers, not what is this? This 10 minutes is the interval between them. It's not numbers of customers. It's the same thing, now wait, the same thing with mu. Mu reflects lambda, right? Mu is like lambda's sibling. It's the average number, again, it's the symbol for number of customers who can be served in the same time interval. The same time interval. So if lambda is speaking about an average of so many customers an hour, mu needs to be speaking of so many customers an hour. The time interval needs to match between them because they're siblings. They're both counts, like head counts. Now, we don't have that information, but we have enough information to figure out in the case of the toll booth what it should be. And at this point, it's really not employing a formula or anything, it's just using logic. Look at lambda. Okay. Cars are arriving an average of 10 minutes apart. That's what it says. Therefore, on average, how many cars arrive in an hour? Lambda for this problem, well, if there's 60 minutes in an hour and they're showing up every 10 minutes, again, I'm just really deducing this, there must be 6 showing up on average per hour. Perfect. It's a count. It's a number of cars, 6. There's lambda. Now I just want to do the same kind of logical deduction for mu. mu. Okay, if the toll booth is clearing cars at an average rate of 1 a minute, well, I mean, I can do this like it's arithmetic, but there's 60 minutes in an hour, so what does that imply? The toll booth could serve up to 60 cars per hour, right? Mu equals 60. Oh, these are the two numbers that we need for this formula, right? Not 1 minus 10 over 1 from here, but 1 minus 6 over 60, 0.9, or just kind of more conversationally, oh, the answer is 0.9 or 90%. Just the result of that formula. Oh, yeah, we can check our understanding with this just by looking at the original data. This toll booth, right, can serve a car in a minute. Cars are showing up an average of 10 minutes apart. That would make sense, actually, that it would spend most of its time, what was our conclusion? It would spend most of its time idle, 90%, because it can certainly serve them a lot faster than they're showing up. At any rate, that's how you get the answer. Now, this next question is similar in that sense. Okay, a system is idle 50% of the time, serves customers arriving at a rate of 10 an hour. Oh, though, similar but not the same. Customers arriving at a rate of 10 an hour is actually a perfect description of lambda. You don't have to do any arithmetic. That's what lambda's supposed to sound like, number of customers per some time interval. Assuming this system fits the description of MM1, what is the average length of the service? Oh, average length of the service. Now you're probably thinking MM1, is that L sub Q? Is that W sub S? Is that P sub 0? You know, all those different formulas? Oh no, wait a minute. The average length of the service? It's simpler than that. It's actually asking us about mu. Right, the service rate. Okay. Well, I was given lambda, but how am I supposed to figure out mu if it's not given? Well, wait, we were given one other piece of information, and that's that the system is idle 50% of the time. Oh, there's that formula again. The proportion of time the system is idle, the probability there's nobody in the system, 1 minus lambda over mu equals 50% of the time. This should equal 0.5. Oh, and we have the lambda. So that should be true. Now we only have one unknown. Okay, let's see, negative 10 divided by mu. I'm going to subtract 0.5 from, or excuse me, subtract 1 from each side. I want it to disappear over here, so that winds up being a negative 0.5 on this side, which means that mu equals a negative 10 divided by a negative 0.5, or, all right, that means it winds up being positive, right? Mu equals 20. Oh, what have I found out? If customers are arriving at a rate of 10 an hour, and in fact this system is idle 50% of the time, then it must be able to serve customers at a rate of 20 an hour. Great, the answer is 20. No, it's not. We're getting close, but careful. That's just not quite the answer. And it has to do with how was the question phrased. It says, what is the average length of the service? And I said, oh yeah, you know, that has to do with mu, but mu's a count. Mu's a count of the on average number of customers you can serve. Oh, we've discovered that on average you can serve 20 customers in an hour. Therefore, it's just logic. What is apparently the average length of service? Well, there's 60 minutes in an hour. You're serving 20 customers in that hour. That reveals, apparently, it takes an average of about 3 minutes to serve a customer. So, this is actually the best answer to that particular question.